Okay, so I'd like to introduce tonight's speaker. Carl Wick is a professor emeritus from U.S. Naval Academy, Department of Weapons, Robotics, and Controls, with 26 years of teaching at the Academy. He also spent a couple of years teaching biomedical engineering capstone courses at Washington University. He has a bachelor's degree from U.S. Naval Academy, master's degree from Naval Postgraduate School, and a Doctor of Science degree from George Washington University. Carl has owned 3D printers for over a decade, and we'll be talking this evening about the largest 3D printer project he'd undertaken, which is amazing. So, Carl, without further ado, it's all yours. Let me go to the next slide here. Take it from there. Okay. Oh, yes. Yeah, if you want to pin it on your stuff.
Let me measure the audience. How many of you have 3D printers? Couple. Okay. How many wish you had? Okay. In case you're wondering, emeritus is Latin for fossilized remains. I got into 3D printing about a decade ago, maybe a little bit more now, because the students at George Washington were in the 3D printing. I figure I better at least get even with it. Since then, I've had at least 3 printers, each maybe a little bit more capable each time. And as a result, I'm always looking for things to do with it. And back in May, in Sky and Telescope, in the back here was an article about somebody who had made a 3D printed telescope. No directions at all, nothing like that. So I thought, well, why not? Why not? I've got a printer. It works really quite well. And so this is my odyssey. I find it ironic that the movie came out here. I'm going to have, go ahead, you stay here and see the microphone. Thank you. I'm going to have Dennis pass around a few things here while I'm talking. Yeah, right. What he's passing around is 3D filament, the stuff, the basic product that you make things out of, and 3 objects that were made from the filament. There's all kinds of plastics now, and some of them are even flexible. For example, that black cover. Okay, let's get started here. So why would I want to build a 3D telescope? Well, somebody gave me the idea. I wanted a telescope with a larger aperture than the one that I have. Larger apertures allow you to see details that you can't see with smaller apertures, like the bands on Jupiter, for example. Now, whether or not it's less expensive is debatable, right? It's less expensive if you have the printer already. A big element is that it is customizable, and as I go along here, you'll see that I approach this project with a lot of unknowns. There's tremendous number of unknowns, and I needed the flexibility to be able to take care of those unknowns. And I actually wound up building this scope twice. First time learning from my mistakes, and the second iteration is the one that you see up here. It's lightweight. This scope, 6-inch scope, only weighs 10.5 pounds. And that's because of the construction that you'll see. The 3D printed construction is lightweight by nature. And of course, it's educational, and my life's been, or a good portion of it's been associated with education. So that was my motivation. You can have your own. Maybe somebody bought you a 3D printer and now you need to do something with it. Okay, I'm going to take a minute here and I'm going to try to bring up this larger. Yeah, okay. I'm going to spend a moment here to talk about the kind of telescope this is. This is a refractor telescope. It works on the principle of refraction. And now, what have I got up there? Okay. Refraction simply is the bending of light. Now, I'm going to give you a disclaimer. Often in engineering, things want to get complicated. Einstein was very fond of simplification. I think taking a lesson from a fellow by the name of William of Ockham back in the 16th century, who was a champion of making things simple. Simple was the best solution, typically. Einstein said everything should be made as simple as possible, but not simpler. Tonight, this is probably going to be simpler than possible. All right, I start with the idea of starlight. So Alpha Centauri is about 4.25-ish light years from Earth. Every instant of that star, photons are emitted all around the star and leave the star as a big balloon might be, getting ever bigger, ever bigger. By the time it reaches Earth, it's gone about 10 to the 16th meters in distance. That's the size of the balloon, the radius of the balloon. We're going to carve out a 6-inch segment of that balloon. That balloon is going to appear straight. There is no angle to any of the photons that come in. So at the top of the screen, you'll see what I call a line of photons that's coming straight in from Alpha Centauri. You're pointed right at it. I'm not going to make it any more complicated than that. All right, those photons that came before it are shown as a red line in the circle. I'm going to try this laser pointer here. And it's not going to work very well, but what we're looking at is right here. Okay, I want you to think of this as a line of children linked together on a playground. Photon next to photon next to photon. Right? They're linked together so that they'll all try to travel at the same speed. Now, there's an interesting property here that photons travel at the speed of light, 300 million meters per second. Very close to that number. Except when they're in something else other than a vacuum. And that something else could be air, could be water. In this case, it's glass that's of great interest. Photons do not move at the speed of light in materials like that. They propagate slower than the speed of light. There's a measure called the index of refraction. The index of refraction is simply the ratio of how fast the photons go in a substance to the speed of light. So a larger number means slower. Larger number means slower. Glass is 1.5, which means it goes about 2/3 the speed of light. Not as fast. Okay, let's get back to the children and the playground. Playground's got a sand pit in the middle. Right there. So we watch as they come down here, and I'm going to move now down to the next. Let me see if I can get. It's always tricky when you try to do tricky things. All right. All right, so here's where we were before. I'm going to start when one end of the line reaches the sandbox. Sand in here. Got to go slower. I'm going to let the faster group continue ahead until they hit the sandbox. Meanwhile, this bunch up here is already in sand. This bunch is going to move farther than this one because they're mired in the sand. Look at the line now. It's bent. When I continue within the sandbox itself, nothing happens until I reach the other edge, and the opposite happens. Now, children at this end speed up because they're back down in the faster medium, and this bunch is still in the sand. This bunch goes 3/2 farther than this bunch. I get another tilt. The effect is I came in here in a straight line going straight down. I wind up going off to the side. Okay, that's refraction. If I choose the angles right, I'll have this situation, and also shorthand. Notice that all I care about is how something came in and how something leaves. Shorthand in optics is to draw a line somewhere in the sandbox, in this case the lens, called a principal plane, and you just make the two lines meet so that you come in this direction and you leave this direction. If I choose things right, if I choose the angles correctly, all of these lines will meet at one point. That'll be on the next slide. The opposite happens over on the other side. All those lines will meet at the same point. The exception is this. The speed is not constant for colors. So although you would like all the colors to have to travel at the same speed within this glass product, they don't, which means that they leave at different angles, which means that they don't meet at a single point, which means that you have a color problem. The way around it is not shown here, but is used in this telescope, is to add a second lens with a different material in which the colors bend the opposite direction. That's called an achromatic lens. Achromatic lens. It's two lenses together. Okay. Any questions? Wow. It'd be helpful if I had this in the right direction. Okay, I'm building a refracting telescope. So I'm going to use the lens. I'm going to use the idea of refraction. I'm just going to take the marginal, what they call a marginal rays, the farthest outside. Everything else in here is still pointing to this one point called a focal point. Each lens system has a focal point in it that is at some fixed distance. And that length from the lens principal plane to this focal point is called a focal length. To make a telescope, what I've got to do is take the starlight that comes in here, take it through the focal point to another lens called an eyepiece, and have it run in the opposite direction. So everything that goes through the focal point of that eyepiece lens winds up going parallel out. So I go parallel, triangular, parallel again. All right. The difference in size here to here is a measure of magnification. And if you go back to your high school or early college trigonometry, you notice that you have two triangles with an equal angle here. And it's pretty easy to come up with a formula that's used, and that is the focal length of the eyepiece, focal length of the objective lens divided by the focal length of the eyepiece is the magnification. So if you buy a telescope, typically you'll have maybe 3 eyepieces. So each eyepiece will be marked with a focal length on it. If you know the focal length of the objective lens, then you can determine the magnification each time. This telescope over here uses a zoom lens because I don't want to have to take the eyepieces out. It does exactly the same thing. I'm showing lines right here that indicate eyepieces with higher magnification, each having a shorter focal point. As I go up here, notice that the field, this objective lens projects down here, the field gets smaller and smaller and smaller. So the expectation is that as you go up in magnification, your field of view is going to get smaller and smaller and smaller. And you'll notice that you begin to look like you're looking through a tunnel. So actually, it turns out high magnification is probably not a super good thing. Usually lower magnifications are something that you want to deal with. All right, another item here that came into play is this. If I have an eyepiece with a shorter focal point, notice that its field of view is really wide. It's actually wider than the information that comes in from the objective lens. So I have field of view way out here, which could pick up stray light inside the telescope tube. One way to combat that is to build a baffle or a donut. And if you calculate where this triangle is going to be in space, it's pretty easy to build a donut here inside the tube to block light coming down, increase contrast. And that's something that I use in a telescope here. Okay, that's enough science. Questions? Yes.
Cross section here, you had under. Does that do anything to like bend light and look around to the field of view? Is it just best to have a clean?
It's best to, well,
Can you repeat the question?
yeah. The question is it best to have a clean edge on the baffle? Yeah. That's an interesting question. Nature typically doesn't like clean cuts like that. So it could produce its own refraction around it. To be honest with you, I've forgotten whether I use clean cut or not on it. One other item here associated with magnification is rigidity. If you have high magnification, that means any movement in here, like my hand, causes the image to dance around. And so what if you're going to use high magnification, you really want to have a very rigid system. and a rigid way of mounting the telescope so it doesn't dance in the wind. All right, 3D printing. It's really dirt simple. You take a filament, and I'm going to pass, not that you have already seen the filament. If you take this filament, you take a nozzle that's heated to 250 degrees, roughly centigrade. It's hot, about 400 degrees Fahrenheit. You force the filament that's been passed around through this nozzle, which I'll pass around. The nozzle is 4/10 of 1 millimeter. It's about the size of a human hair. You're going to have trouble seeing the hole in this nozzle. The plastic comes out and is forced down either onto a heated substrate or it's forced down onto the layer that's already laid on the heated substrate. And this just happens over and over and over and over again. The layers typically are 0.15 millimeter, about a third of the opening of this thing that I pass around. It's incredibly small. So that means that printing has got to be done really quite quickly. But the process is really simple. There are many kinds of plastics now. I use 3 kinds of plastic, or 2 kinds of plastics in this. The 3 kinds I passed around, one is called PLA. It's a lot like Lego plastic. It's easy to work with. It's got lots of colors, but it's easy to work with. It's got lots of colors, but it's not very hardy. If you have it on a hot day like today, good luck. I use PETG, which is a shorthand for chemical formula. PETG is much hardier. It can handle temperatures. I've built devices that have been outside for years, and they're still holding up on a PETG. And the third kind is a relatively new plastic. It's only been out a few months, at least from the manufacturer of my printer, TPU. And TPU is flexible. It's the same kind of stuff that you give in a Croc shoe or something like that. Not a lot of colors, but it's really great for doing things like lens covers and such, and dampers. All right, there are some constraints in printing, particularly in a project like this, and that is the printer architecture and speed. You need to have a printer that's really pretty quick because it's going to take a long time if you don't. If you figure that you're laying out about a quarter of a meter of plastic tall, each section, the bigger sections in there, it's going to take a whole day to do. This printer takes about 10 hours to run a section of the size that you see. The more important thing is the architecture of the printer, and that's the so-called X, Y, and Z. A lot of printers print in the X direction, and then the head moves up each time in the Z direction. But the bed goes in the Y direction this way. So that's not so good for a tall object, because the taller you get, the more unstable the print is. And if you have a sharp enough motion in the Y direction, you can actually topple that piece, and that ruins the print. There's no recovery from that. You just have to start over. The printer that I have uses the opposite kind of strategy. It does X and Y on the print head, and Z only moves up and down. So there's never any of this toppling motion or potentially toppling motion. So the next thing is build volume. In my printer, which you can see a picture of up here, I'm right at the maximum build volume. And actually you can see it's laid down a couple of layers here. This is the base upon which the print would be printed. My particular printer has got 4 print heads, each potentially holding a different filament. They're lined up over here. One filament is attached to the print head right now. All right, so we got a printer. You need software with the printer. There's two kinds of programs, and it really depends on where you get the print files from. If you do them from scratch, which is what I've done here, then you need a CAD program, a computer-aided design program. That's where you draw up a solid object. Once you have the solid object, you need a program that's specific to the printer. So each printer will undoubtedly come with a program called a slicer. And the slicer's job is to take this solid object and carve it up into layers, each 0.15 millimeter high, and then describe what the print head has to do on each and every layer. And that turns into a file called a G-code file. So G-codes are codes that tell the printer, hey, in this layer, you need to print a circle such a size. You need to print another circle representing the inside of the object. Then you need to print a lattice work in between, and that's how we keep things light. So this is a partial print of an object that was passed around here. We're many layers up, but it's showing you the inner skin and the outer skin, and the lattice work in between. These things right here are called supports, and they're used because of the following limitation on a 3D printer. 3D printers don't like to print over voids because the filament, if the void is large enough, the filament will sag. So a way around that is to print supporting structure that essentially gets broken away at the end. There are 3 holes that are printed up in the upper part of this part. And that's what the supports are doing. So they're printed along and eventually you just throw them away. Yes.
Use those 3 different types of filaments, but we use 3 different types of filaments for this.
On the total project.
So,
No, 2 different types, PETG and TPU.
so you do the sections of different filaments, or
That's all the same.
I mean, I just wasn't sure that when the painting with the filaments, I mean, they couldn't be so small, as each filament is using individually. So it can start to use types of filament.
Yeah, basically you just use 1 filament at a time.
So it makes a better perspective. So it's, and how do you put the 2 different filaments into the abstract?
Oh, there's, I guess the question is, how do I load up 2 different filaments?
To print out this.
Well, each of these devices in the back is a print head. And associated with the print head, each print head is a reel on side. And this filament gets fed automatically up through a pipe up to the. I'm not answering your question.
Well, no, I get that part. I guess I'm wondering is when does it switch from one filament to the other?
Oh, that's part of the G code. G
So
code,
the different
G code
sections that we
knows.
put it-
Right, sorry. Yeah. So the question was, how does this thing know when to switch from one filament to another? And that's in the G code. So this is a picture of the Autodesk Fusion CAD that I use. There's lots of CAD programs around. You use it to draw up a sketch in 2 dimensions. And then you can either grow it up. There's a way of growing up into 3D, or there's a way of revolving a sketch around to get a 3D product. The CAD programs are very capable now. They can even calculate what you need to, what's needed to print threads. And that's how things are connected together in this telescope by threads. This is a slicer. Slicer goes with the particular printer that I have. You take that drawing, you pass the file to the slicer. You answer a few questions about what kind of filament you're going to use, what orientation you want, and then you push a button, and it does everything else for you. Slices it up, dices it up, generates the G code, and this particular slicer will even send the G code via Wi-Fi to the printer, and you can say go. So it's basically automatic, and I've learned to trust it over my own intuition.
Well, so the green thing there, is that one of those supports?
That's one of the supports.
So those stay there until it's all done, and then you just rip them
And you
off?
just snap them off.
Okay.
Yeah.
That's just to keep it solid until it's all done?
Well, in this case, there's, you may not have even noticed, there's 3 holes up there. The holes, in order to have a perfectly round hole, need some support. Otherwise, at the top of the hole might sag.
Okay.
So
So that whole, okay, I get it.
So this thing grew this tree from the base all the way up to where the support is needed.
So you didn't have to drill that hole?
I didn't have to drill a hole.
Oh, wow, okay,
No tools involved. It's a
okay.
screwdriver and an Allen.
Are all the filaments, do some filaments not work with other filaments? Or do all these different numbers of filaments, do they all work well with each other? When they're meetings, they like each other?
Yeah, pretty much. It's pretty seamless.
Any question?
The question is whether things work well together, and the answer is yeah, that's pretty seamless. Yeah. You take a file, a particular file type, and move it into a slicer. It'll accept it and do the slicing in very short order. It doesn't take very long at all. We're talking seconds to do a job that's actually, I find, quite incredible. It also knows how to orient a part so that you minimize things like the sag and so on. And I've learned that it knows best. Okay, so I got a couple of minutes here. I'm gonna talk my way through what I had to do to build this thing. I've got a picture of refracting telescope up here to kind of give you. All right, it's not gonna, apparently didn't find it. That's all right. All right. I went online, AliExpress, Chinese company. Bought a 6-inch lens, about $300. It's a gamble. Week later, I get it in the mail, wrapped in Chinese newspaper. No directions whatsoever. It's a two-part lens, because it's achromatic. Right? It's got a very thin metal washer that goes in between the two parts, but there's about 4 ways you could put it together. So I wound up, after fooling around with it for a while, I wound up going back to the company and finally getting some direction on what you were supposed to do to put the two together to make it work. All right, now I got a problem though. The focal length is measured from the principal plane, but I don't know where the principal plane is. It's somewhere in that 2-lens system. I don't know where it is. So I got to have some room for fudge factor, and that's where the focuser comes in. So how to get even close? Well, the very first thing that I printed up and put together was what I'm going to call a lens cell, and that's the light gray part up in the telescope. And inside there is the lens pair backed by a screw-on ring to hold it in place. Now I don't have lenses falling all over the place. I can put this on a table in my basement, shoot it out the back door to some object as far as I can shoot it. Take an eyepiece that I already had, go about 750 millimeters, which is what the focal length was supposed to be, and fish around a little bit until I could get an image. Now I know how long to make the tube. I don't want to make a focuser, so I went to a different company, Gina Astro, good company. Focuser about $150, I think, something like that. It's a really great focuser. It's good value. So now I have the length of the focuser. I know how long it can extend. What I want to do is build tubes in between so that I hit about midway on the focus. That way I've got maximum slop one way or the other. So that's what I do. I create 2 tubes that screw into each other, that screw into the lens cell. The second tube has a baffle that's at the very beginning edge, so I don't have any overhang. I can have it flat on the base, the substrate, so I don't have to worry about it bending at all. And start printing. Lens cell, probably about 6 hours worth of printing. The 2 tubes that you see in there are both about 10 hours of print time. And that's a fast printer. So then I have the remaining length. This is the original one here. The remaining length to get me to focus, and I can focus on the trees in my backyard, and so now I'm reasonably close. Unfortunately, if you use this and the focuser alone, you're always in a horrible position trying to look through the scope, because you're always trying to look down the tube. It's much nicer to have what's called a star diagonal, something that brings the image out at right angles. The problem is, I don't know how long that star diagonal is. So I go online and I find some estimates of what it might be. And so I reduce the size by that much, 70 millimeters in this case. And now you have what you see up here. So this whole thing just screws together. And now also I determined I need to be able to have this thing mounted rigidly. And I need to be able to find a center of gravity, balance point, if you will, because the mount sort of wants that to happen. And this thing is very end heavy because the lens weighs about 6.5 pounds. But the whole thing only weighs 10.5 pounds. So I have a piece of aluminum channel that I had. I calculate how much of a buffer I need to have it attached to the bottom in both the forward tube and the back tube. And I print that extra margin with the tube. Hey, you can do anything with these printers, any shape that you want, any shape anywhere. That shape required, however, that I have support because it's up in there, right? It doesn't start at the base. The holes I needed to drill, I don't drill. I just have them printed. So that's how things got attached together. When I finished, I got my first reel of TPU, and the obvious thing to make with it is a lens cover and covers for the aluminum channel. So that's the story. Took it out when Jupiter was in the air and got a good clean focus on Jupiter. So I think we're in good shape.
So it all started with the Chinese lens, and you had to build and calculate everything around that Chinese lens.
Yeah.
Yeah.
Questions?
I don't know if this, I'm asking if this is possible. If there's like a polycarbonate that you're going to lay and could make that decision, so if you possibly manufacture your own lens.
Wait, say it again.
Is your is a 3D printer, maybe not necessarily yours, capable of manufacturing the lens?
Oh, no. There isn't anything clear enough yet. The clearest that I've seen is I have a reel of glow in the dark, which almost would make it, but not quite. Yeah. That would be an interesting thing. If there was something clear, you could probably make a Fresnel lens, at least. That seems like that's something that might be possible. But I do not know of anything clear enough to do that. Yeah.
Got two questions. How long did it take, like start to finish, and what was the biggest challenge for you?
Yeah, how long did it take to start to finish? Not long, about 2 weeks maybe. Something on that order. The biggest challenge was figuring out where the focal point was. That was the biggest challenge. Everything else is relatively straightforward. There's not much involved in a refractor telescope. Not much. Now, I did have issues with tolerances with fitting the lens in the capsule. So I did have to screw around with that a bit.
Any other questions?
What's your next, have you thought about what your next, like, project will be? Now that you've built this amazing telescope?
The answer is no.
It's incredible what you can do with them.
Oh, absolutely, yeah.
We
I,
were watching a show where they were building homes with a 3D printer. It was using cement, liquid cement. And it was massive 3D printers. It's incredible.
oh yeah, they're great, and they're great fun. They're great fun. This article that I have, the guy in the article was thinking about building a mount next. That's pretty ambitious. Requires great strength. You have to have a pretty rigid design too. So I don't know. We'll see.
Maybe a little question. You mentioned that when you are, you're building these things and you have to have those support, little support things that you end up breaking away. Okay, I can imagine I'm breaking it away and breaking the thing itself. I mean, so it's breaking away that simple?
Yeah. Yeah, it's just snap. That program, the slicer, knows how to do that exactly right. And any time that I fooled around with it, I got lousy results. You notice that it looks like a tree, the trunk. If you notice well, let me go back. Yeah, that's called tree supports, and sometimes depending on what you do, they branch out. They actually branch out. There's another way of doing it that is lattice work, and that doesn't work so well here. That's why I trust this thing now. It's an option, but it doesn't work as well as what the program recommends. Yes.
That was a 3D printer cost.
Yeah, it's sort of all over the map. Depends upon what you want. If you want one that's like this one here is like $800 or $900 now. It's not that expensive. Sometimes the printers will have multiple functions. Sometimes they'll have a laser module associated with it too, so you can do laser cutting and engraving using the same mechanism. That might be a bit more. But this is purely dedicated to 3D printing, filament printing, multiple colors, does them all at once. This was done all at the same time. This is kind of interesting because if you spun it around, you see that it's a bunch of gears. They work pretty well. The gears pattern is a chevron, like this. There is no way you can build one. It has to be grown because you can't force a chevron gears together. They don't go. So that's the precision.
How many filaments did you have to go through to do that?
That's one roll.
Just one roll for the whole thing?
One roll for the whole thing. Yeah. I used two different colors. So one roll for all the gray and the light gray, only a portion of one. Yes, sir.
Question with the gears with the balance. I understand how you would have to make that decision to be each layer that way. There is a little bit in this beautiful way, of course, but there's a little bit of play, way more than we can tolerate in amount.
Yeah, that's so they don't glue themselves together when they get printed. Yeah.
So if you were to make a mount for your telescope, would you have to manufacture each individual part and assemble it yourself, or do you think it's possible?
You might be able to squeeze the tolerances a little bit closer, maybe. But I have actually done a mount, but it's been years ago. And it was for a different application for a satellite antenna. And I didn't use this kind of an idea. I used worm gears. And the CAD programs will print worm gears. They'll print gears for you. So anything is possible these days. Anything. Well, thank you for your interest.